5.3, Poisson probability distributions. A Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. So a specified interval. Usually that's going to be like a time period, some period of some years. The random variable x is the number of occurrences of the event in an interval. The interval can be time, distance, area, volume, or some similar unit. Got a formula for this, and I know it looks kind of complicated. The probability of the event occurring x times over an interval is given by this. Now remember, mu is talking about the mean, and e is actually a number. We're a lot more comfortable with pi. Everybody knows pi is about 3.14. E is about 2.72 or so. So we've got these symbols. We've got a factorial in there. It's a pretty complicated looking formula. Just make sure you've got it written down somewhere. All right. Requirements for the Poisson probability distribution. Number one, the random variable x is the number of occurrences of an event in some interval. 2, the occurrences must be random. 3, the occurrences must be independent of each other. And 4, the occurrences must be uniformly distributed over the interval being used. Parameters and properties. We've already talked about the mean. And we can also talk about the standard deviation, which we've seen this formula for standard deviation before. Square root of the mean here. Properties. A particular Poisson distribution is determined by the mean. A Poisson distribution has possible x values of 0, 1, 2, and so on and so on. Number 1, Atlantic hurricanes. For the 55-year period since 1960, there were 336 Atlantic hurricanes. Assume the Poisson distribution. So we can see this interval, this time period of 55 years. So that's kind of a hint that it would be a Poisson distribution, other than the fact that they told you it was. Part A says find the mean number of hurricanes. There's not a lot of information in this problem. 336 hurricanes over 55 years. We're just going to divide. So the mean is about 6.1. 6.1 hurricanes per year, right? Part B. Find the probability that in a randomly selected year there are exactly 8 hurricanes. We want to find P8, where Px is the probability of X Atlantic hurricanes in a year. All right, so remember this formula for the Poisson distribution. It was the mean to the x power times e to the negative mu over x factorial. Really complicated looking formula. But now let's just find P8. So for finding P8, we just let x equal 8. We found the mean a second ago. Mu was 6.1, so we're going to have 6.1 to the 8th power times e to the negative mu is 6.1 over x factorial, so 8 factorial. So you want a calculator for this. Let's see if you can type that in and get the right answer. I would practice if I were you. Shouldn't be terribly difficult, I don't think. Hardest thing probably is finding that E button. And also the factorial. Type that in. Hopefully you're getting what I'm getting, about 0.107 or so. We can see this is about 0.107. Okay, so think about what that is. That's P8. That's the probability of exactly 8 hurricanes in a year. All right, about a 10 or 11% chance of 8 hurricanes in a year. So moving on to part C, in this 55-year period, there were actually 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in part B? Well, okay. So let's recall. What we found in part B was this. There's a probability of 0.107 of having 8 hurricanes in a year. So we want to look at 55 years. In 55 years, the expected number of years with 8 hurricanes is 55 times that probability, 0.107. So let's calculate that. And we see about 5.9 years. Or 5.9 times. Okay, there'd be 5.9 years with 8 hurricanes. Okay, that's what we've found. All right. So keep in mind, we would expect 5.9 when there was actually 5. That's pretty darn close. So our 5.9 is pretty close, reasonably close. This 5.9 is reasonably close to the 5 times it actually happened, so the Poisson model seems to work well. Poisson distribution as an approximation to a binomial probability distribution. The Poisson distribution is sometimes used to approximate the binomial distribution when n is large and p is small. One rule of thumb is to use such an approximation when the following 2 requirements are both satisfied. N is bigger than 100, n times p is less than or equal 10. If both of these requirements are satisfied, we want to use the Poisson distribution as an approximation to the binomial distribution. We'll need a value for mu. And so this mu We might have talked about this in the last lesson, but mu is equal to n times p. Remember, with your calculator, when you do a binomial distribution, you can do binom PDF or use that website. But we're kind of talking about the same thing. It's not the same thing, but sometimes we can use the Poisson to approximate the binomial. Example 2, main pick 4. In the main pick 4 game, you pay 50 cents to select a sequence of 4 digits, 0 through 9, such as 1, 3, 7, 7. If you play this game once every day, find the probability of winning at least once in a year with 365 days. So we can see the interval here. You're playing every day for 365 days. But in order to do this Poisson distribution, we're going to need to start with the mean. And we have this formula for the mean, mu equals n times p. N is just the number of times that we're going to play this game, which is 365. P is going to be the probability of winning. You're going to need to go back to last chapter to think about the probability of winning this. Okay, think about guessing someone's PIN number. If they don't have Face ID, if they've got a 4-digit code. You know, if I was trying to guess this PIN number or this main pick 4, look at it like a fundamental counting principle problem. 4 blanks for each of the 4 digits. 10 choices, 10 choices, 10 choices, 10 choices. So that's 10,000. The probability of guessing it right is 1 in 10,000. So it doesn't come out and tell you the probability here. You have to use some of your techniques and figure that out. So we want 365 times that. .0365. Now that is the mean, or the expected value. So I guess that's the number of times I would expect to win. Okay. So now let's do the Poisson. But one more thing. We've seen this a couple of times here recently. We want to find the probability that we win at least once. And that's going to be very, very difficult to calculate directly, because at least one means you win 1 time or 2 times or 3 times or 4 times or 5, 6, 7, all the way up to 365, and we'd have to add all those things up. There's a much easier way that we learned. Do you remember this? Instead of adding up every single one that I want, I could subtract off what I don't want. And we've seen this before. At least once, we can say that's the same thing as 1 minus none. And that's what we want to do. We're calculating this indirectly. Instead of adding up what I want, I'm subtracting off what I don't. So 1 minus P0. We're going to have this 1 minus, and then that P0 is going to be our Poisson formula. X is 0. So the Poisson formula says mu to the x power, so mu to the 0, times e to the negative mu. Well, I guess I could plug that in, couldn't I? Well, let's back up here. We found mu. Mu was 0.0365. So to the 0 power times e to the negative mu over x factorial. In this case, x was 0, so 0 factorial. Now, please notice this denominator does not cover the 1. It's going to be 1 minus this fraction. But one thing that's nice about this fraction is that 0 really simplifies things, because we know something to the 0 power is 1, and we know 0 factorial is also 1. So a lot of this ends up falling out of the problem. you really only end up with e to the negative 0.0365. About 96%. Now don't forget, it's 1 minus, what was that, 9642? 1 minus 0.9642. There's a 96% chance that you don't win at all. So you subtract there, subtract, and you're going to get 0.0358. Now, one thing that's tricky, I think, is that result is so close to the 0.0365 result we got before. I think that's purely coincidental. Now, earlier we talked about how this is an approximation for a binomial. So check it out. I did a binomial PDF right here. 365 was my n number, 1 in 10,000 was my probability, and I picked 0. And I got that same 0.9642 number, or really, really super close. 0.9642, same thing. So we can do the same thing. 1 minus 0.9642, we're getting 0.0358. That's the probability of winning at least once. Example 3, Powerball. I feel like this is the exact same question. So this is overkill, maybe a little bit. There's a 1 in 292,201,338 probability of winning the Powerball lottery jackpot with a single ticket. Assume that you purchase a ticket in each of the next 5,200 different Powerball games that are run over the next 50 years. Find the probability of winning the jackpot with at least one of those tickets. Is there a good chance you would win the jackpot at least once in 50 years? Your gut probably tells you no, but let's look at the numbers. Start by finding that mean. N is 5,200 because that's the number of times that you're playing this game. The probability is going to be 1 in 292,201,338. So if you type that in to your calculator, you're going to get about 0.0000178 or so. That's the expected value. So then we do kind of the same thing as what we did before. Notice we won it at least once again. Going to win at least one time, maybe 2, maybe 3, maybe 4, maybe every single time. We're adding all of those up, or maybe it's going to be easier, instead of saying at least 1, to say not none. So again, we're going to have the same kind of deal. You're going to have 1 minus this Poisson distribution. So that's mu to the x power, x was 0, times e to the negative mu over x factorial, 0 factorial. Going to look like that. Keep in mind, again, that denominator is not under the 1. You have 1 minus that. Now, again, this to the 0 is 1, and this factorial is 1. So essentially, all you're doing is 1 minus e to the negative 0.000178. .999982 or so. Just call that 9999. Well, now you know what I'm going to call it. We've got 4 9s and an 82, let's say. 1 minus 0.999982. We get about 0.000018. That's the probability of winning it at least once That does not seem very likely. Is this likely? No way. Not likely.